Okay, so they're going to give us a statement. Okay, in this case, like I said, the if is an implied if, and the then is implied, so they don't necessarily write them down. But our goal is, okay, this first one here, this first if, that's a given statement. You know that to be true. And we talk about our hypotheses in conditional statements. The if part is true. That's the, if I close my eyes or just have this thing on my desk, that's what I know to exist. That's what I know to be true. The then part is then the conclusion that you can make once you have that thing in your hand. If I have 2x plus 9 equals 19 in front of me, if I know that's true, then what allows me to go to this? Because this is true as well, right? If this is true, this will be true, okay? The 2x equals 10 will be true. But what allows me to know that it's true? What did they do from step 2x plus 9 equals 19 down to 2x equals 10? Good, okay? So what we've got here is subtraction property of equality, okay? And that is the answer to the question of why do I know 2x equals 10 is true? Does that make sense? And as we go throughout this course, that's going to be one of the most important things that we can do is ask the question why. Okay, and not just this course, but other courses, and especially the further you get in mathematics, being able to ask why is almost more important, if not more important, than being able to do something. Okay, because if I ask that question why, it starts the ball rolling in regards to being able to show why. I start to show why. And I make an argument, a valid argument, to really show and demonstrate the proof of something. The idea is that piece of information I just proved is going to stick with me much longer than if I would just memorize it. Does that make sense? So if I give you, we did this a couple weeks ago. We proved the distance formula, okay, and showed how it is created. Hopefully, going through that process allows that distance formula to stick with you a little bit longer than it would if you just purely memorized it, okay? And that's really what's going to happen here when we do proofs is we're going to expose ourselves to some information, some procedures that allow our properties and our theorems and our definitions and our constants and all the information that's encapsulated in those things to stick with us a little bit longer, okay? And hopefully stick with us forever, or at least until we don't need those things outside of high school anymore. Okay. Part B there, question B, says the same type of thing. Now this was algebraic. This is geometric. Okay. So we start with if, and I get then. Okay. So if angle O is congruent to angle W, and angle W is congruent to angle L. Okay. What allows me to make the jump straight from O to L? You remember that property, Warren?
Oh wait, the property?
Yep. What were you going to tell me?
I was going to say because the hypothesis and the equation were the same.
Careful, because these aren't, like that statement there is not exactly the same as that one, right? I think you're trying to use, and we will do this eventually, I think you're trying to use like the law of detachment and stuff like that. We will do that later in some of the proofs, but we need multiple lines really to do that. That's the transfer property. Good. Okay. Somebody in the last class, or maybe it was, I think it's actually fifth period maybe, they said, well, I know angle O is congruent to angle L because both O and L were stated to be congruent to W. Does everybody recognize that? Well, if two things are both equal to W, then those two things must be the same to one another. That's great. That's 100% right. Okay? But that's kind of a pain in the butt to write out, isn't it? So we take that idea and say, okay, that whole idea, if I have two things that are congruent to the same thing, I can actually say that those two things are congruent to one another. That whole procedure is wrapped up and said, called transit probably, just something so we can talk about it a little bit easier. Okay? And that is kind of the pain in the butt with some of this stuff, is that these properties, people understand them and they recognize them kind of in like layman's terms or general terms, but then we have to link to it some geometric or algebraic name so we can talk about it a little bit easier. Okay? So if I had to sit up here and say, well, O and L were congruent to W, they were both congruent to the same thing, so I can say they're both congruent to each other. I had to say that every single time we come across a transit property throughout the entire year. That's all I'd be saying. Okay? So we want to encapsulate that and call that the transit property. If you remember from the video, it was an idea where we said, let's see here. In the video, they call that A, they call that B. Okay. Well, if W is B, it's got to be B there, right? And then L was some arbitrary C. And A, B, and C, they could be numbers, they could be shapes, they could be people, they could be rooms. It doesn't matter what they are. Okay. They're just things. Okay. If one A is the same thing as one other object B, but B is the same as C, we can make the link then. If those things are true, we can make the direct link that A is the same thing as C. The way I like to do it, and you're going to see us do this in some of these questions that we do on that worksheet. A equals B, B equals C. So we have if, we really have two pieces of information with that if. We get a then that we make the argument A equals C. If A equals B and B equals C, then A equals C. What I like to do, wow, I wrote it too fast, so hold on a second. I like to put them this way. Okay, if A equals B and B equals C, then A equals C. And then I like to merge them together because the B's overlap, right? So now I've got A goes to B, but B goes to C. So I can eliminate the middle part, and what am I left with? A equals C, right? Okay. So every time that, and that's something that I'm not saying it's the right way to do it, I'm not saying it's the wrong way to do it, but my mind sees that progression of moving things, merging together, and wiping away the middleman. Yes, that B is the middleman. Wiping that away, and what am I left with is now a new true statement. Does that kind of make sense? And that's what I think you guys should probably start developing on your own, is ways of visualizing some of these properties and how they work, because that transit property is going to be something we use all the time. Okay, it's a very, very useful property. And the last one, if the measure of angle E equals the measure of angle T, then the measure of angle T equals the measure of angle E. Does anybody know what that one was from yesterday? Really doesn't say anything new, right? Okay, and really maybe where you would use this before in the past would have been like if I'm in algebra class and I have like 3 equals 2x plus 3. Okay, you might have preferred to rewrite that as 2x plus 3 equals 3. We know we can do that, right? We can flip it like that. Okay. Does anybody know what the property is for being able to flip something? Flip an equation like that? Starts with an S. Symmetric. Okay. Remember, symmetry means that the left-hand side is the same as the right-hand side, right? Okay. Think about the symmetry of your body, where the right-hand side is supposed to be, or is somewhat similar or symmetric to the left-hand side. So that's what's going on here. Okay, if I have the phrase, if measure of angle E equals T, then measure of angle T equals the measure of angle E, because that's exactly what this is saying here. Okay, they imply the if and then. What I could do is I could put in a line of symmetry right there. Got ahead of myself. There should be a measure of angle T there. If I put that blue line of symmetry and I fold on it, does angle T land on angle T? Does angle E land on angle E? Does that make sense? Okay. So that idea of just flipping an equation around, okay, is the symmetric property. We don't use that a whole lot in this course. Maybe throughout the year, maybe 5 or 6 times. We see it once today, but it's not a huge property that we use in this course. You use a lot in Algebra 2 and you use a lot in pre-calculus, but not so much in this course. Does But those are some of the properties that, some practice of the properties that we want to talk about. But now inside a proof, what a proof does is it starts to layer those things on top of one another. So we might have 4 or 5 different things, like A, B, and C all together at once. Okay. My suggestion to you is to go through a couple of these other slides here in this PowerPoint and work with those properties. The hope is that we see a lot of them in the next couple of days, that they just become second nature to recognizing when the transit property, when substitution, that kind of stuff happens. Proofs, that's kind of what we've been trying to build towards. This whole chapter has been trying to build towards these. And we're going to introduce them, and this tends to be something that people struggle with until it's too late, or they don't recognize this until it's too late. But proofs are not something that's going to show up today. We work on it a couple days, and then they disappear. Okay? Unlike a lot of things maybe you do in high school, right? You see it once, you deal with it for a short period of time, and then it goes away. All right? And you learn something new, deal with it for a little bit, and it goes away. Proofs are pervasive through all of mathematics. Okay? And in this course, we're going to deal with them in Chapter 2. We'll go away from them when we start Chapter 3, start talking about some things in Chapter 3, but then they come back in Chapter 3. And then we'll go to Chapter 4, we'll learn something that's not really proof-related. And then in Chapter 4, towards the end of it, we'll start talking about proofs again. Okay? So every chapter has some type of proof work inside it. Okay? Because every chapter is going to give us rules. Okay? And these rules are called theorems. They're if-then statements that are true facts. Okay? And they're different than postulates, because postulates we had to accept as being true. Theorems we can prove true. So when they give me a theorem, every time they give us a theorem out of the textbook, we will take time to prove it and say, why do we know it to be true? I don't want to just take this author's word for it. Okay? I don't want to take the teacher's word for it. I want to know logically, step by step, why we can make these statements. Okay? And the hope is that if we do that, you're going to understand that statement a little bit better. You're going to understand the preliminary statements that help build that a little bit better. And then that geometry is a little bit more solid in regards to your understanding of it. In addition, if that doesn't convince you enough, proofs are going to be on the end of course exam. There's usually between 2 and 3 of them. Okay. That being said, you say, well, that's not a lot. Well, if there's only 15 questions, it's quite a bit of the test. Okay. So you're going to see proofs on the end of course exam. So hopefully develop a skill for you to be successful on those. What happens is, proof is just a convincing argument of saying why something is true. Okay, if I'm a lawyer and I'm trying to maybe defend my client, okay, maybe my client is being prosecuted for murder or something like that. Okay, if I'm trying to defend him, don't I build a case about that person? Maybe I do some character witnesses. Maybe I start doing alibis and stuff like that, and I try to prove that guy was not able to have committed the murder at that time. Okay, but if I'm the defending lawyer, and I'm able to show that this guy's a great guy, he had no connection with this person, the murder weapon doesn't fit him or was never found, but I can't give the jury any information on where my client was during the time frame of the murder. Is that a gap in my argument? Yeah. And what's the prosecutor going to do then?
He's going to be like, got any proof?
Yeah, he's going to attack that hole in my case, right? I'm going to try to tear that apart, and then it's ultimately up to the jury. Okay. What we want to do mathematically is make sure that there are no gaps in my logic, so nobody can attack it. Okay. Much like a lawyer would do, so it's that kind of thought patterns that we want to go through. When we write proofs, okay, proofs are, if I were to ask you guys to write a paper about what's a book you guys have read in English class?
Mice and Men.
Okay, if I asked you to write a book about mice, how many freshmen? All right, so we won't talk too much about Mice and Men, but it's a pretty good book, right? All right. So we won't give anything away.
Wait, what?
But if I was going to write a paper about Mice and Men, you're going to do maybe an outline, right? Start to structure your thoughts, okay? Then you're going to put that into a rough draft, and then you're going to have somebody edit that, and you're going to put it into a final draft, right? With proofs, we're going to do the same thing, okay? We're going to develop a rough draft, okay? We're not going to do we're going to do an outline. We're not going to do a rough draft. We're not going to do the final draft. But we're going to organize our thoughts. And this is a visual up there of what most of our proofs are going to look like. They're called two-column proofs. They're going to give you a given information and prove statement, okay? And they come from some conditional statement. So they're saying if measure of angle 1 equals measure of angle 3, prove then that measure of angle AEC equals measure of angle DEB. Okay? Every theorem we come across this year is going to be written as an if-then statement. The if part, when we want to prove that theorem, the if part becomes the given, and the then part becomes what we're trying to prove. Okay? So down the road, we might try to prove, see if I got one of these open yet. Chapter 3, we might try to prove this thing right here. Well, the first thing we're going to do is we're going to find the if part, which is that right there, and that's going to be my given. The then part, that's going to be my proof. Okay? So if I was going to set this up, try to prove this theorem, I would say something like this. Okay? And that's what this stuff in red is showing me right there. Okay? I usually need in a proof, I need at least some concrete things to talk about. So if they talk about adding two angles, I want to name two angles I can add together. If I talk about two parallel lines, I want to talk about two specific types of lines. Okay, give them names. So the if part is the given, and the prove part is the then of any theorem. Okay, so when we come back to this, that's where we're getting this information right here. They're giving us some statement, some theorem. If measure of angle 1 equals measure of angle 3, then prove that those two angles are equal. Measure of angle AEC, measure of angle DEB. You always have a picture. Okay? At least like 95% of the time you'll have a picture. Okay? And then on the left-hand column, we have our statements. And this is where we're kind of doing our algebra. We're doing law of detachment, law of syllogism, that kind of stuff. Piggybacking statement after statement to create new statements. Okay? Here it says each statement should follow logically from the previous statements. Okay? And then over here are the reasons why my new statements are true. And those reasons might be because of definitions. They might be because of some postulate. They might be because of some theorem. Or some of the properties that we talked about in the last couple of days. Okay? So there's going to be, what really happens, what people struggle with, is this column here. Okay? Because you're going to have a collection of many, many things at some point. You know, if we think about it right now, we're 5 weeks into school. We probably have 30 to 40 definitions. We probably have, looking at those properties from yesterday, there's probably 15 to 20 properties. We've probably got anywhere between 10 to 15 postulates. And that's just in 5 weeks. So we've probably got maybe 70 to 80 different things that could come in those regions. Does that make sense? At Christmas time, that list might be 800 things. Okay? And that's kind of the dynamics of this class. And what's hard about it is we might introduce something in Chapter 2, but in 7 months from now, can we recall that information from Chapter 2 and use it inside a new proof? Okay? So that's it's a terrible assumption on the part of any educator to assume that once you've seen something, you never forget it. Okay? But that's kind of how a geometry course is structured when we deal with proofs. And any math course is structured when you deal with proofs. Once you've seen it, it's understood that you know it and that you can use it and apply it. And that's kind of the battle that we'll have this year is can we continue to use that old information, regurgitate it, reuse it, reapply it, and hopefully not forget it. Okay? This here, I'm not going to walk you through that step by step right now. Maybe tomorrow or the next day we will. But I suggest for you, especially if you start having trouble with these things, go home, print that off, get on a big piece of paper, and put it in your math binder, math notebook. Tape it to your computer or whatever, something, so that you have this, because this will always get you kind of unstuck when you get into a situation with proofs. Okay, and ultimately, what that will do, if I have a proof that's 6 steps, that'll probably find me 4 or 5 of those steps. If I have a proof that's 13 steps, that'll find me 10 to 11 of those steps. Okay? Now you'll have to have some creative thought to find the missing steps, but this will usually get you unstuck, okay? And you want to follow that step by step. Again, we'll talk about that tomorrow, but I want to get into some specifics, some examples here with this stuff. So turn to that handout. And this is, I didn't give you one yet, right? I'm sorry. I knew it. I didn't want to because I gave it to the last class and some people started working on it right away. Try not to go ahead in this. When I give you guys handouts, guided notes, that kind of stuff, don't make the assumption that you know exactly what you're needing to do and that you just try to get this done. Because there will be some times where I assign it for homework, and if you did that, it also needs to be done. There's also times where I skip around, and you might do 4 or 5 proofs that we never talked about. It might be kind of wasting your time, wouldn't it? So try not to do that. When we have proofs, I like to do, as many as we can. I think the more we expose ourselves to them, the better we're going to get at them. So I hate to give maybe 1 proof every chapter or 2 proofs every chapter. I like to do as many as we can. So what allows us to do that is me printing them all for you. Right? We would hate to sit here for 3 or 4 minutes and let you copy that down so that we can actually do the problem, right? So you'll get a lot of handouts. If they're not handouts, they'll be, I'll let you get your computers out and download the PowerPoint, and you can type stuff into the PowerPoint. But keep that handout. We're not going to get all the way through it today. We'll work on it tomorrow. We'll probably work on it the following day as well. But there's a series of proofs on that I want to talk about. You have done some of these, okay? And throughout the day, I've asked every class, how many of you have seen something like this or done something like this? And usually, 2/3 of the class raises their hand and says, yes, I've done this. So I'm taking the assumption that the other third is just forgotten, okay? You guys have taken in the past an equation, and you've gone through step by step and solved that equation, right? Do you remember then providing reasons why those steps were able to be conducted? Okay, I'm seeing some head shake, so that's good. What I want to do here is just remind us, okay, initially when we start doing these proofs, I'm going to put that if and then in there, but eventually when we start doing these on our own, it's just going to be assumed if and then. But they're saying if we start you off with 3x plus 12 equals 8x minus 18, if that's what we're starting with, okay, can you then prove logically, okay, with properties and theorems and definitions and all that kind of stuff, that x is equal to 6, okay? Hopefully we all understand the process, and this is where I get concerned mathematically for students is that, yeah, we can go through step by step and do it, but do we know why we're doing what we're doing? Okay? So I think if we understand why, we're going to be much better at solving equations when things vary a little bit, when they change the equation slightly. Okay? The first thing we're always going to do is write down our given information. We have to start from somewhere. We have to start with at least one true piece of information. So that's the given information. Okay? So that's presented for us. We know it to be true. And now everything else, all those other reasons on the right-hand side, should be properties or definitions or postulates that we've learned in the past. Okay? So this is how we kind of approach this initially with algebraic proofs. I got an if statement, and now that line is a then statement. So what allows me, if I know the if part is true, what property allows you to say that the then part of the conclusion is true, Mallory? Good. Subtraction property. You simply took that 3x and moved it away from that 8x, right? And so we subtracted 3x from both sides, so that's the subtraction property of equality. Okay? This is going to be kind of a task sometimes to write things out. Okay? Sometimes we'll have to write out sentences. Sometimes it might seem like to write a paragraph out for some of these reasons. So if you want to develop a shorthand tool for yourself, abbreviating things, that's fine. Just make sure that, like for subtraction, I go far enough to where it doesn't get confused with substitution. Because the goal is for you guys to use these as notes, to look back upon them in 2 weeks, 3 weeks when you're preparing for a test or quiz. Or maybe I'll let you use your notes on a test or quiz, because that I've been known to do that. Okay? And if it said SUV, you've got debatable on what you meant when you first did that. So make sure you don't abbreviate too much. Okay. So now we're here with an if-then statement. So we drop down a line. Okay. So if 12 equals 5x minus 18, then why does 30 equal 5x? What they do there? Anybody? Yeah, they added 18 to both sides. And when I add something to both sides, that's the addition property of equality. Okay? Whenever we do something to both sides, it's of equality. Okay? Because we're maintaining that balance in the equation. Okay? So now, we start with this as being our if statement, and that is our then statement. So if 30 equals 5x, then 6 equals x. What did they do there? Division. Good. And finally, they didn't really do anything new in regards to the information gained, but if we start with 6 equals x and get then x equals 6, what property is that? Anybody know? Good. Symmetric property. Okay. And the way I remember this is, if I wrote this way, if 6 equals x, then x equals 6 is what we gain. If I draw that line of symmetry, fold on it, x is laying on x's, 6 is laying on 6's, so it does kind of give you that visual of what symmetry is supposed to be. What I want you guys to understand and gain from this stuff is that you might have to sit and ponder something and think about something for a while. Okay, it might not just come to you naturally. Okay, right? Instantly get the answer. Okay, and that's what people struggle with. Is that I don't get this. I don't understand. I'm not getting as fast as my neighbor is. My neighbor does one of these questions in 5 minutes. It takes me a half hour to do one. That's just the way it is. You'll get better at it. Okay, but understand that there's times. I have when I do a proof in one of my classes, I have to read it, mess around with it, go to bed, wake up the next morning, deal with it a little bit more, come to school. Okay, make some free time, work on it a little bit, go home, look at it, go to bed. Okay, it might take 3, 4, 5 days before I really recognize it and something clicks for me to be able to answer that. Does that make sense? I might have to research. I might have to ask a lot of questions. So those are things that if it doesn't come natural to you, don't worry. It's okay. It won't come natural to a lot of us. Eventually, the more we expose ourselves to it, the more questions we ask, it will make sense to you. Okay? And please don't think, because I know some of you might have this concern that, man, we do it in class real fast, and it makes sense in class, but when I get on my own, it's totally mind-boggling. When I was in your seats, I had the same issues. When we did it in class, awesome, I understand exactly what's going on. But when I got home, I didn't have a clue, okay? And my sister probably hates me to this day because she was really good at this stuff, and she basically taught me how to do it, okay? So don't think that, you might think this in other classes, that the teacher, it's so easy for them, okay? I have empathy for you. I know what it's like not to be able to understand this stuff. But if you persevere, if you continue to work through it, it will come to you, all right? But you can't just give up. If it doesn't make sense day one and you just quit, then that's on you. And you're not going to understand it ever. This one, I wanted to do this one because what I want you guys to realize is that Rylan might do a proof one way. Okay, Sarah might do it another way. Jay might do it a third way. Rylan might have 9 steps. Jay might have 5 steps. Sarah might have 7 steps. But every one of them is 100% right. Does that make sense? Okay. So you've heard the phrase, there's more than one way to skin a cat. You heard that before?
No.
You ever heard that?
You skin a cat?
No, I don't. I don't think you're allowed to. But there's more than one way of doing something. Okay. And in proofs in general, there's a lot of different ways of doing it. Okay. Pythagorean theorem. Okay. I think there's documented 79 legitimate ways to prove a squared plus b squared equals c squared, and it always works. Okay. So there's a lot of different approaches, okay? So just because yours doesn't match your neighbor's doesn't mean you're wrong or they're right or vice versa, okay? If I do something in class that doesn't look like what you've done, or maybe I add 2 steps, or I left a step out that you had that you thought you needed, present those questions to me. Ask me, okay? Do I really need this? Do I not need that? Why don't I need it? Why do I need it? That kind of thing, okay? It'll help you understand things a little bit more. I think this one, I don't think anybody is going to, when I ask you to solve this equation here, I don't think anybody consciously does maybe those steps right there. Okay, 3, 4, and 5. Okay, but I want to talk about how we can structure proofs to be maybe a little bit different than what our neighbors look like. Okay, so if I start with statement number 1, that's obviously given, right? Okay. What do they do if that's my if statement and that's my new then statement? What do they do from statement 1 to 2? Yeah, they distribute, okay? Somebody in the last class said multiply. Is that what distributive property is? Yeah, so if you said multiply, I have no problem with that. But remember, in Math Excel and the end of course exam, if they ask us to do a chart like this or a proof like this, there might be like drop-down windows to choose from, and multiply might not be there. Okay? It might be a distributive property. So understand that they really say the same thing. Distributive property just multiply multiple times. So we did distributive property of equality. Okay. Now, just to kind of speed things up a little bit so we can get this done before the day's over. Hopefully you see from line 2 to line 3, nothing changed other than the flip-flop of those 2 terms, right? Okay, so that and that were the same. These 2 things, 12 and 12, 12 in and 12 in, and 27, 27, they're the same. But I flip-flopped the 28 and the negative 3 in, right? Does anybody know what property allows you to do that when we talk about adding things? Say again? Not substitution, not symmetry. Say again? You're on the right track. The other one. Commutative. Okay? Commute. If you ever listen to the radio or watch the news in the morning, they might say, maybe you're getting on I-75, they might say, watch out, your commute is maybe delayed by a half hour because of a wreck, something like that. Commute means your movement from A to B, point A to point B, right? From one position to the next position. So the word commute means to move, and that's what we're doing here. Okay? So we're commutative property of addition. Okay? We're moving the negative 3 in and the positive 28. And we know then, like, for instance, if I take 28 plus negative 3 and then negative 3 plus 28, I get the same result, right? So that's what allows us to move them around. So whenever you see things that have been just moved around, it's the commutative property. Okay? Now, Sarah, what is different between statement 3 and statement 4 now? Okay, so they group the 20 in and the negative 3 in, right? And when I group things, it's what? That's the associative property. Okay? The way I remember that, don't abbreviate it, but the way I remember that is when you are with your friends, they're your associates, right? Okay? And when you're with your group of friends, it's a group, it's a cluster of things, and that's what we're doing when we put parentheses around something. We're trying to group it or cluster it and say those things go together. Those are a group of friends, so they associate with one another. Okay? Those are very, very important properties through all of mathematics. Commutative property, associative property. Okay? Step 5. Okay, so we're going from here to there. Now, most people, throughout the day, not a whole lot of people have gotten this until I ask them kind of a prompt, but really nothing changes, right? You know, the 12n minus 27, that's still on the right-hand side. The 28, still got the parentheses. But now I've rewritten negative 3n as plus, or minus 3n as plus the opposite of 3n. Do we know what that is? If If I'm going 20 minus 3, is that the same thing as 20 plus negative 3? And maybe in 7th grade, 8th grade, 9th grade, you were taught that subtraction is adding the opposite, right? Okay. Subtraction is the same as adding the opposite. And that's actually how we define what subtraction is. Okay? So I'm going to write here that this is the definition of subtraction. And the reason I wrote that, I just wanted you guys to see that on that right-hand side, in our reasons, we get definitions. We use definitions a lot. Okay? And once we start getting into the geometry aspect of this, that side is going to be riddled with definitions. And that's where it becomes important to know our vocabulary, right? If I don't know half my vocabulary, I'm not going to know half my reasons. Okay? So as we see new vocabularies, make sure that we are picking up on those things. Now my hope is that when you guys are doing these, okay, if I were to just give you the equation and ask you to solve for n, you're probably not going to do those 3 steps, right? Okay? But when you take the 20 in, what the information that you have right here, 20 in plus 28 minus 3 n equals 12 in minus 27, most people are going to jump straight to step 6, right? But the reason you can jump straight to step 6 is because of 3, 4, and 5 being true. Okay? And we cluster those in the same, maybe like combine like terms or simplify or something like that, right? That phrase, simplify or combine like terms, means something. There's a logical progression of why we can do that. And that's kind of what we talk about with proofs. This is kind of like if somebody was reading this proof, hopefully it's very detailed so nobody can attack it. It's very detailed so like if somebody knew very little about math, they could follow it. When you guys write a paper for an English class, don't you write it to your peers? Okay, you write it to people that are kind of want to read that, right? Either your English teacher or the person that's going to edit it. You don't really write. If I'm going to write a book or a paper about Of Mice and Men or Kill a Mockingbird or something like that, I'm not going to write that to a 3rd grader, am I? No, I'm not going to write it so a 3rd grader can understand it because they're not going to read it. Okay, so as I'm writing proofs, it's the same idea. If I'm a college professor, I got a PhD, and I'm on a sabbatical writing papers and doing proofs and that kind of stuff, doing research, I'm not going to write a proof to a 9th grade geometry student. Does that make sense? Yeah, I'm going to use language that is read by my peers and understood by my peers. Okay? When we do these proofs, the mindset we want to think about is that we're writing it so I can explain something to my neighbor that has the same level of knowledge that I do, or less than that. Okay, so maybe I'm writing this to somebody that has absolutely no understanding of math or no understanding of geometry, and they should be able to follow along why it's true. Does that make sense? Okay, so that's kind of the way you want to think about it. And as we go throughout the year, people are going to say, well, why'd you add that step here? Okay, why do I need that? And sometimes my answer will be, because I want to make sure that nobody gets lost, nobody gets confused, and they can follow from one step to the next. What do you do then from 5 to 6? Yeah, they actually did that addition, didn't they? Some people are saying combine those, right? But through addition is how we combine them, right? So I'm just going to say addition. Okay, now I'm not. It's not of equality because I didn't do it to both sides, right? So I either add them, or if you want to say combine like terms, or if you want to say simplify, that's fine. I just like to be a little bit more specific with which operation I did that simplification with. What do we do from line 6 to line 7 now? Corey? Jalen, that's fine. Subtraction, right? You guys can just throw out answers, doesn't matter. So they moved the 12 in to that side, right? So I got subtraction, property of equality. We did that to both sides, so it is of equality. Now, what would have been okay? Say Jalen would have done that way. She moved the 12 in over that way and got 5 in on the left-hand side. But let's say Corey moved the 17 in over with 12 in. Would that have been okay? Yeah. Okay. So that's an example of where one person does it one way, another person does it another way, and they're both still right. Okay. Their proofs would be different, but their work would still both be right. What do they do then from 7 to 8? Subtraction again. And why? The reason I developed it this way is so that we can see sometimes you will have successive reasons of the same statement or the same argument. Okay? And then how do they go from 8 to 9? Good. Division, property of equality. Okay? So that's an algebraic proof. Okay? In the other classes, we did get to a couple of the geometric proofs, the early ones that maybe take 2 or 3 minutes to do. But I think that's a good start for us. Just in the mind frame of what we're doing with proofs, we're trying to answer that question, why. Tomorrow, we'll use that packet again, and we'll get into the geometric stuff. Make sure you don't lose that packet, because I didn't print off enough to give you one tomorrow again.